Oh, hi there. Hey guys, what's going on? Memes here. Oh my god. It's showing that we're only at one bar. That's alright, it's alright. This is a working session. This is session what? Like number 8. I'm trying to catch up on my project and at least finish like the generalized first half and everything. So let's not dilly-dally anymore. Let's just bring up the stuff. Yep, this notebook, make sure we got all the stuff and things here. Okay. Alright. Okay. So now. Okay. There we go. Alright, current. Current it is. Let's do our little deep dive. God. Should have just gone through this all like last week or so. I digress. Alright, let's share our whole screen. Alright. We got that there. Alright. And then let's get up our, let's go, I think we, hold on. Let's move this dude over here. Here we go. Alright. Alright. Don't mind the arbitrary stuff and things over there. Alright. I think that was the guy we were trying to do. Okay, okay. Oh, the code. Wow, so many errors. Oh, did I just put this in that whole thing and not send? Okay. Shift, enter. Run it. Oh god, that's terrifying. Hopefully it can... So it's the computer, maybe it won't get mad at the single words. I know I would, so I'm not expecting it to. Alright, so let's go on to our last little thingy we have over here. Balances and... Oh god, all the history. Kilogram, this do-it-yourself balance, the future. Alright. Disseminating the new... What? Shouldn't expect to use a kibble balance. Alright. Shouldn't expect to use the way they're bananas in the supermarket, but the change will be useful to many industries. Mash measurement capabilities are much more sensitive. I'm sorry, I know. 1 milligram to 1 kilogram is a multi-step process. A comparison of uncertainties. Yeah, the IPK copies. Yeah, having to have that platinum iridium cylinder lying around. Hopefully it doesn't get a chip. Yeah, air buoyancy. Solving it if it's 10 microns or 10. Okay, it's vacuum chambers. Okay, so that's more the methodology of measurement. All right, cool. So the ampere. All right. The quantum meteorological triangle. Okay, we'll have to get to that. All right. The ampere. The story of the ampere began when Danish physicist named Hans Christian Ørsted. Oh, the Ørsted. I think that's a unit. Discovered that magnetism and electricity were two aspects of the same thing. In 1820, he showed that you can make a compass needle deflect from north by putting it near an electric current. As Ørsted discovered, current in a wire produces a magnetic field and encircles the wire and affects other nearby fields, such as those of a bar magnet. A French mathematician and physicist named André-Marie Ampère was inspired by this demonstration to work out the connection between electricity and magnetism. Found that if you put two wires parallel to each other and pass current through them, the wires will either be attracted to each other or repelled, depending on whether the currents flow in the same or the opposite direction. This is because each wire generates a magnetic field. The longer the wires and the higher the currents passing through them, the greater the magnetic repulsion or attraction. Until 2019, the SI definition followed this arrangement. It were set up under ideal conditions with these wires exactly 1 meter apart. A current of 1 ampere would result in a force between the wires of 2 times 10 to the negative 7 newtons. That's not much, roughly a 10 millionth of the weight of an average apple. But it's there. Each wire carries a current of 1 ampere in the same direction. All right, so you got 1 meter, 1 amp. 1 amp, current flow, infinitely long and thin wires in the oh, that's a negligible circle area. Okay, so assuming under idealized conditions, the force is 2 times 10 to the 7. Hence, 1 ampere has approximately 10 to the minus 7 newtons of potential force there. I believe that's the correct thingy that we go by, but all right, let's go back here. All right. Okay, so we need a history. Okay. So Orsted, when was Ampere? Hold on. Ampere person. Hold on. It should be within the definition. Okay. French mathematician, physicist. All right. When did they do that? Let's see. Where is that? This current is. That's interesting. Okay, so they chose this would be conveniently sized. Former definition. Let's go over here. All right. Do they have when it was? Since power is defined as the product of current and voltage, the ampere can alternatively expressed in terms of other units using the relationship I equals P divided by V. So that would be current equals power divided by voltage. Thus 1 ampere is 1 watt divided by voltage. Current can either be measured by a multimeter device, so can measure electrical voltage, current, and resistance. Well, I've used one of those. That's what that actually is doing. Is it doing the right thing? That's all we really cared about, or at least. All right, infinite length. This is a attractive repulsive force between. This force was used in the formal definition after giving the vacuum magnetic permeability, magnetic constant mu naught, a value of exactly 4 pi times 10 to the minus 7 henries per meter, equivalent to n over a squared. That is newtons divided by amperes squared. Hold on. Newtons divided by ampere squared. What does that give us? Magnetic permeability, not in a named unit system. That's interesting. Mass light. Okay. Is that supposed to be ampere constant? It should have some dimensionality. Well, that didn't help. The Biasia constant's essentially the same thing. Newtons per... Is that what it is? That has to be what it is. Is henries over meters. Henry over meters. Magnetic permeability. But it has a thing. Wait a second. Oh, Newton per square ampere. Okay, now it's saying something. That's what I did, right? Huh. That's interesting. Enter basic unit. Okay. Gauss per Oersted. See? See? That's when our friends pop out. Okay. All right, let's go back. All right. Techniques to establish the realization of the ampere had a relative uncertainty of approximately a few parts in 10 to the 7. Involved realizations of the watt, the ohm, and the volt. That's interesting. So the ampere, this is previous, okay. So what they're saying is there may have been a very slight deviation around the 7th decimal place I'm hearing. That is interesting. I'm just gonna hold on to that. And now it's literally defined by elementary charge, which we know that very well. And expressed in the unit big C, Coulomb, which is equal to amperes times seconds, where the second is defined in terms of the hyperfine transition of cesium-133, the unpreserved ground state, blah, blah, blah. So in charge of Coulomb is the quantity of electricity carried in 1 second by a current of 1 ampere. Okay. Conversely, the current of 1 ampere is 1 coulomb of charge, which is a lot of charge. Yes. Oh, that's where that number comes from. Going past the given point per second, or equivalent to the 19 elementary charges every 1.62 seconds. Oh, wait a second. You're just taking that number and 10 to the 19, you're plugging that number in there. But you're just changing that to seconds. That seems like something I would do. Okay, so this was confusing me before. This actually kind of makes sense. Constant, instantaneous, and average current are expressed in amperes, as in the charging current is 1.2 amperes. And the charged accumulator passes through a circuit over a period of time expressed in coulombs, as in the battery charges 30,000 coulombs. It's the same. The relation of the ampere equals coulombs divided by seconds to the coulomb is the same as that as the watt. The watt equals joules times divided by seconds to the joule. Huh. That's neat. You know, it's derived from the ampere. Electric charge. Cool. It's derived? You're basing it on... Well, being defined using these SI derivatives can either be given special names or defined in terms of their meters per second. Yeah. Hertz, joule, watt, candela, lumen, lux. Can be added the prefix. Yeah. All right. Yeah. Okay. I'm just saying when its definition is literally I don't know. Is this the circular logic we're looking for? I don't know. You all have to tell me. All right. Yeah. Okay. hold on. I got current. Ampere. No. All right. Where are we? Okay. With the discovery by Hans Christian. We want to get it right. It's the person's name. That'd be like calling Euler Euler. God, who would ever do such a thing? Me. Two aspects of the same thing. Electricity and magnetism were two sides of the same coin, so to speak. And let me see. And that putting a compass semicolon. Putting a compass near a chart electrical current would deflect the needle from magnetic north. Okay, is there any more stuff on Ampere? Okay, that's literally the thing. Laid the foundation, created the modern electrical science, International Convention, exposition of electricity. Alright. Cool. Ampere was originally defined as 1/10 of the unit of electric current in the centimeter gram second system of units. That unit is now known as the ampere. Was defined by the amount of current generated by the force of 2 dynes per centimeter of length between 2 wires 1 centimeter apart. Okay, the size of the unit was chosen so that units derived from the MKSA system would be conveniently sized. Deposit per second from a silver nitride leader. Measurements for needless currents about. Okay. Alright. Okay. Alright. I mean, without getting into the effects, I mean, this is actually really short. Okay. So, and then, oh, I gotta actually do the thing with the dude's name, right? Yeah. Okay. North. Okay. Let's go back here. I'm procrastinating. French mathematician. Inspired by Orsted's work. Oh God, I'm not gonna get all those things. I'm just gonna have to copy and paste. I'm sorry. A French mathematician and physicist. I don't want to piss off the method. I'm like, hey, that's how it is, and I think M comes before P, and I spelled them both wrong. Wow. French mathematician and physicist. Or so it's work. André Marie Ampère, French mathematician, physicist. All right. Sought to figure out what was going on between well, actually, you can't really say it other than electricity and magnetism. Huh? He found that running current through a wire would generate a magnetic field around said wire. And thus, having two wires next to each other would attract oh my God, I can't spell at all. Spell check has ruined me. Attract or repel depending on the direction of the charged currents. Alright, file, save as. Alright. Save to cloud. Save early, save often, my friends. That's because when it disappears, then you go into panic mode. Alright. And it needs to be infinitely thin because you want it to be a constant force, and if electricity is going, I don't know, like 137th the speed of light or so, yeah, you're probably going to run out of wire pretty. Yeah, you want an idealized experiment, something like that is like what they say. Pardon me, I know it's getting a little bit late, but okay. Hold on, I'm realizing I need to add something to kilograms. Mechanical quantity. We give an exact value, the best measures obtained worldwide. Average reliable repeat or measure H. Okay. Okay, well that wasn't very useful. Let's see. Where are we? Okay, so when we say it's, how exactly is it defined? It's just counting. Okay. CLA and H is that. Yeah. It's frequency, but V is not V, like you knew. H is what's known as Planck's constant. All right, yeah. Packet's energy. Taking the two equations together yields a countertuple huge mass. Even though the scale average is related, yeah. Planck first used to describe the vanishingly small amount of photons, blah, blah, blah. Joule is the energy. Linking mass to H with extraordinary precision became possible in the late to two different physical constants that relate to voltage and resistance. The Joseph's constant. Okay, voltage. Okay. Okay. That's a silicon atom. All right. Above said method. All right. Okay, so then setting an exact value, aka defining it 10 significant digits for the most part, should be pretty good. All right. And that's where, yeah, that's where we got the modern value, and we got what? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think there's 1, 2, 4, 5, 6, 7, 8, 9. I think there's 10 digits. Go data. Oh god. We got Planck's constant. Wow, I've been saying this wrong for a while. 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh. Wow, I've been giving an extra digit credit. Okay, then I guess we had to 11 before. Take back all my ramblings before. Wait a second. Okay, why does H bar have 10? We just divide it by 2 pi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe we had enough digits before. Okay, well, H bar we have 10. Planck's full constant we have 9. Is that because this is like what we're like actually using and we're just doing the circle to the other? That's kind of weird. Okay. And now I know. And knowing is half the battle. Isn't that right, Jax? Well, hey, no, I need to catch this up because I need to submit this stuff by like next Tuesday or Wednesday, and I still have the extra half of the project to go through. trying to nail down some relevance within the Wolfram model. I, I've contacted at least most of the relevant people. We'll see if they're around, if they can help, and if not, I will speculate rampantly. I'm okay with that. Yes. Yeah. Oh my god, Jax is returning in different forms. I don't even know what to do. You got cacti and smiley faces here. It's okay. It's okay. It's all right. Oh, I mean, I see nothing. Yes, John Cena. You don't. Oh God, that's annoying. Seeing my own face and oh God, there's like three of me here. Hold on, I need to swap to something better. Okay. Oh wow, we just basically increased that by like 5 or 6 fold. Okay. Not that I see. I'm learning because people start sharing stories. It's like okay, that story. I think it was actually this because I literally just had to read through most all of this. Okay. Ugh. I need to hydrate. That's okay. Back to the amper. Let's finish this off. Okay. Alright. And then originally, when did it... Alright. And then... People continue to work all the rules and system per current, voltage, resistance, hour use different unit system. At one point, there were 4 different systems. Use site. Okay. All right. All right. So. All right. Through. All right. During the 1800s, a number of different unit systems for charge related phenomena were utilized. This made things quite confusing for scientists whom in 1861 electromagnetism. I should need a round charge. Well, for electromagnetic related phenomena. This made things quite confusing for scientists who in 1861 had 4 simultaneous systems in place. That sounds like it could cause a few issues. I mean, it's not like unit systems have caused potential. Apparently, when I tell the story about like the Mars lander, apparently it wasn't supposed to land. It was supposed to be a Mars orbiter to basically check out like what was going on the surface, and apparently it's like, hey, we did the calculations in meters. We programmed it in feet. No more. like a $250 million error or something. Oopsie. It's probably more than that. I'm sure there's more to the story, but it was contrary. Hey, of course, why wouldn't we do it a different... Hey, Imperial's never caused confusion before. Okay, I need to start babbling. All right. Oh, it was in Chicago. All right. So let's see. In 1893, a scientific committee called the International Electrical Congress, IEC, met in Chicago. Settled two units to be the basis for the others: the ohm for resistance and the ampere for current. The Congress's decision was formally accepted at the International Conference of Scientists, who met in London in 19... Okay, oh, I pronounced that like the conference, the International Conference of Scientists. God, that sounded pretty pompous. Apologies. All right, so... the International Electrical Congress... I see. Met in Chicago in 1893. Hey, we have to differentiate it a little bit, but I mean, like, how it's pretty much computationally reduced. 1983 to okay, to decide on a single decide on a standard for EM related affairs. All right. They chose 2 units. The ohm, and that should be capitalized, ampere. The ohm and ampere representing resistance and current respectively. Alright, that should minimize my blatant plagiarism. Okay, I should probably actually throw this down here too. Okay. So about use the calibrate voltometer. Oh God, all these people are absolutely mad lads playing around with such electricity. Hey, Titan. Welcome, my friend. No, we're just finishing up stuff that I should have done like a week ago. But, yeah, no, just going into the deep lore of units. See, at least this is a lot more straightforward. I mean, it's fascinating. I'm not an electrical engineer nor physicist, but I'm like, wow, this makes sense, rather than the mole that broke me yesterday, even though our SI definition kind of broke the mole. And the dang candela! I'm sorry, I've been raging to everybody about it. It's like, wait. You did a redefinition of SI to make it more coherent, to literally base our base reference units on constants of nature. Why? Because we want to be accurate. Yet the candela alone is the one thing that literally has no fundamental basis with a constant of nature, unless you consider an English sperm candle and the human eye constants of nature. I wish I was making it up. The definition is hold on. Okay, I'm sorry. Where was okay? So this has been updated. Okay, it's hold on. Let's do the first definition. In 1948, the candela as defined as the luminous intensity in the perpendicular direction of a surface of 1/600,000th square meter of a black body at the temperature of freezing platinum under a pressure of 101,325 newtons per square meter. I mean, isn't that obvious? I mean, I'm doing. I watched The Guild, I think, was the last kind of thing like that. I have heard good things about solo leveling. I think after I finish up these summer camps and stuff, I'm probably gonna have to binge some of that. But I've been doing just over at the Wolfram Summer School trying to finish this off, and oh god, I should have be finishing right now. I'm sorry. Hold on. Let me save me. Okay. So is there anything else on that history? These are units. Okay. Subsequently, hold on. Subsequently adopted by adopted at the meeting in London in 1908. Okay. National Bureau of Standards, the progenitor to NIST. Alright, temperature, blah, blah, blah. The ohm was one of the first units to be created for electricity. He's arguing one of the easiest electrical quantities to imagine since wires never relates. Yes, I actually can remember at least the first couple of digits. Why? It's 29.9792. Why? Oh, excuse me. No. That's a unit. I was just expressing hot garbage. The Planck. Oh God, what is this one? Hold on. What does it say? Ohms. Planck impedance. Planck impedance. Yes, that one. I spelled it wrong. There we go. Planck impedance. Oh, lucky. Within ohms. Those are the digits to the speed of light. How very interesting. Hold on. Divide by C. Oh, look, you get 10 to the negative 7. Oh, look, you get 1 amp per constant. Oh. How very neat. Is that why it's supposed to be 10 to the 7? I mean, hopefully It's precisely 10 to the 7. Otherwise, we might have a wee bit of kink in charge, and that might throw all types of stuff off. Not for the scope of this project. Um, uh, yeah, but here's the thing. It's like I could have just had the thing just read all of that, but who cares? It's like this is also like for my own knowledge and stuff, and if I'm gonna try to do like find something in the Wolfram physics project, be like, oh, here's the energy contribution from a single causal edge there. At like some sub-Planckian scale that we're trying to like figure out or hypothesize or parameterize. I don't even know. That's why I'm like, smart people, help. All right, let's continue. But realizing the Ohm standard was a circuitous process. From 1860, the Siemens mercury unit, denoted by electricity passing through a 1 meter long column of pure mercury to use various electrical fluents such as coils, inductors, capacitors. Finally, in 1990s, the phenomena based on quantum. Okay, hold on. It's arguably one of the easiest, since wires of different lengths for zone can carry different amounts of resistance. Standard was a circuitous precision process in the 1860s. It's not the ampere the scientists use today. Instead, this ampere was transformed from definition into practical reality with a device called a silver voltmeter. The international ampere. International ampere. Oh, God. That is what it said, didn't it? Okay. Former was based on. Okay. Realizing. Okay. Was realized ampere called international was not the ampere that scientists used today. Instead, this ampere was realized transformed from definition into practical device calls. This device contained electrodes with positive anode and negative cathode terminals. The anode was suspended in a solution of silver nitrate. Ah, the mass of the cathode before. Oh. Wow, that's crazy. Okay. Generally. When did they change that? Other instruments, yeah. I can produce the same voltage. Resist. I can use the primary standard for. Oh. Wow, literally just. It's like a cotton candy machine. You dip the thing in, you see how much delicious silver gets on it, and. Yeah. The idea of the ampere balance was that technical pass current through coils, physical motion. There's an indicator on the mechanicals. Okay, so that's the other one. Okay. Originally known as the International Ampere Okay. The ampere color was not the ampere that scientists use today. Alright. Alright, so let's just double check here. Okay. It's 2 down. The size of the unit. Alright. That is a crazy one. Hold on. Alright. It's actually less than 1 ampere. Okay. The international ampere. Was determined by a silver voltmeter a device with positive and negative terminals. By a device with positive and negative terminal suspended in a solution of silver nitrate. That's current passed through the device. Silver would accumulate on the cathode. And researchers could weigh the device before and after. Thus, the original or international ampere was defined as okay. Cool. Save. Okay, Western cells, calibrated, okay. Now used as an electronic kilo, okay, so that's... This all right. Allowed precise calibration of future technology such as the Gibble Gibble balance when we talk about mass. Let's see, kilogram. Okay. Physical motion, I guess, only current cause, finding a better ampere. If only had the ampere as a unit of electricity, making it the fourth SI unit, showing units distance time match, which have been incorporated by the time, and then, okay. The ampere was formally accepted as the fourth unit into the General Conference on Weights and Measures, CGPM, 1921. There we go. So we set it as the fourth SI unit. We need to get better. Something just grumbled. Silver voltmeter. Proceeding. At the time of this conference, it was the opinion of the delegates from this country that the volt should have been chosen in place of the ampere because the standard cell was more reproducible than the silver voltmeter was a means and now actually employed in conjunction with the ohm for measuring the ampere by the drop-in potential method. The decision of the conference was, however, accepted as final. Researches were undertaken in several different countries, and particularly in this country, the aim of making the voltmeter worthy to bear the responsibility imposed upon it by the London Conference. Ooh, ooh, ooh. It's an absolute system which used the more fundamental units of the centimeter, gram, and second, which made recommendation of review unanimously approved this decision. Okay. When you say, what's the term, which made would be reviewed unanimously. Review that comments from waste made. That would be viewed after the hideous Sterling World War II. National Committee for Science stuck up the rolling again in 1948, adopted the new definition of the ampere related to the force per unit length of two wires. This harkens back to the original experiments. So they're trying to use science. Okay. I feel like this is important because if you're going back and forth. Okay. Oh, they never actually did. Okay. Between 1933 to 1935, CGPM the recommendations that would be reviewed. CIPM. hold on, CG, PM, and the International Committee, another committee, weights and measures, the IPM, considered basing the ampere on more fundamental units as the CGS, centimeter gram second. This did not officially happen as World War II caused as World War II happened, and in 1948 SIPM adopted the new definition, which was basically Ampere's original definition. Excuse me. All right. All right. So at least one more thing we need to do. All right. Hold on. Okay. Almost done. All right. All the SI, including the Emperor, was used in various mechanisms divided into volt. 22 divided. Yes, as a practical matter, the derived volt and ohm were used to measure the Yes, as a practical matter, the derived volt and ohm were used to measure the underlying ampere. There's excellent reason for that. But the volt and ohm were known with far greater accuracy. That's because their values are right based on constants derived from fundamental effects in the realm of quantum physics. As a result, a volt can be relied to an uncertainty of 6 parts in a billion. The ohm to 2 parts in a billion. This is a catch. Ohm's law doesn't quite have the footing to say Newton's laws of motion. That is, I equals V divided by R. Current divided A equals voltage divided by resistance can't be deduced from other laws of physics. Instead, it represents a seemingly unvarying relationship among the 3 electrical quantities as measured by various techniques around the world during the past 2 centuries. The form is called empirical law because it's based entirely on observational evidence. To a date, it appears that Ohm's law successfully describes measurement made with uncertainties in the range of parts per 10 million, according to one report. Still holds in nanowires, 1 atom tall and 4 atoms wide. So far, so good. All right. Okay. Need some quantum metrology. All right. Ampere, the quantum metrology triangle. Electric current, voltage, resistance are quantities we experience every day from power lines to outlets. Many of them can be described by the 19th century laws of classical physics. But does the time-offered interrelationship described so succinctly by Ohm's law remain true in tiny physical systems, one that operates according to strange rules of quantum physics? Finding out will require experiments in which voltage, resistance, and current are all exactly defined according to principles of quantum mechanics. Before 2019, these experiments were possible in practical terms for the volt and ohm. Both were derived from other SI units according to their formal definitions. Their actual magnitudes were based on two quantum electrical phenomena that bind on fundamental constants. The Josephson effect, predicted by physicist Brian Josephson half a century ago and confirmed shortly thereafter, occurs when two superconducting electrodes are separated by a tiny gap or barrier. That configuration is called a Josephson junction. In ordinary electrical conductors like medical wires, current only moves when pushed along by a voltage. In superconductors, however, current can flow across the barrier in the absence of any applied voltage, thanks to interactions between pairs of electrons governed by the rules of quantum mechanics. Josephson junctions are formed in circular pits. They look like an element of a muffin tin. Muffins? But if a superconducting junction is exposed to electromagnetic radiation, that's microwaves, then a quantized voltage develops across the junction that's proportional to the frequency of the radiation. That proportion is expressed by the Josephson constant. So 2 elementary charge divided by h bar, where E is elementary charge and h is Planck's constant. Quantized means that only specific values of voltage can exist, proportional to those constants instead of a continuous range of values. Ooh. Because radiation frequency can be controlled with extraordinary precision, Josephson just could produce exact levels of voltage with uncertainty in the range of 6 parts per billion. Not surprisingly, Josephson Wolfram standards become the de facto universal tool for calibrating voltage measurement. The other phenomenon is the quantum Hall effect, when a current of ultra-cold electrons so thin it is, in effect, a two-dimensional sheet, is exposed to a magnetic field perpendicular to that sheet. All right. Electrical resistance across the width of the current stream develops in exactly quantized steps. The magnitude of those steps are described by the von Klitzing constant. Okay. There's where it's getting interesting. Okay, so we already did that, yeah. The constants, electrical metrology. Zero values in our okay with zero uncertainty. It's a strange situation. The standard values of all known existed, in some sense outside our sight. Okay. That. Okay. All right. We're going to basically just put this down here. I was going to say, wait a second, didn't we do that? All right. Let's see. All right. The ampere is interesting as it was in part determined by two other more well measured constants. Of nature. The Josephson constant, von Klitzing, discrete values exist in electrical resistance. Okay. Alright. Got that. Okay. By experience, the constants are so important, so they were incorporated as conventional units. Okay. Standard values of volts exist in some sense outside of SI. They're primarily based on the values of constants different from the ones which they're redefined SI base. Okay. That changed immediately. Okay, of Planck's constant elementary charge, which have exact values now. Okay, now the answer is redefined in terms of elementary charge. All three components of Ohm's law are finally formally interconnected by the two fundamental constants. Using any two to determine the value of the third, one can reveal, for example, whether Joseph's constant is really exactly equal to. Oh. True SI values. They're using. Oh. Now that the ampere is redefined in terms of elementary charge, all three components of Ohm's law are finally formally interconnected by only two fundamental constants. All right, H and E. Science is now able to use the quantum metrology triangle, Ohm's law, in quantum terms to check the values of current, voltage, and resistance by using any two to determine the value of the third. That can reveal, for example, whether Joseph's constant really is exactly equal to 2E over H. Any discrepancies would have a major impact on electrical metrology, not to mention quantum theory itself. Everything is fine. Everything is fine. It's not like one little thing can throw a lot of stuff off. It's okay, so this allows scientists to utilize Ohm's law in Ohm's law by using the new definitions to relate elementary charge, Planck's constant. Yeah. Elementary charge and Planck's constant. To verify current and voltage values. So Ohm's law empirical M. Hold on, where was that empirical? Probably should actually to Ohm's law. I equals V divided by R. Current equals voltage divided by resistance. I think that's right. Note. All right. Ohm's law is empirical, i.e., it is based on experimental deviation if there was a small deviation. Let's just put a if there was a deviation, the downstream effects. Oh, downstream. Ah, there we go. Ah, current. Dun-dun-dun. All right, it's a good time for me to get out of here. The effects could be downstream effects. So to speak could be immense. There we go. That's a nice little note. All right, file save. Let's do another save. We'll save it again as something else. Why? Because we can. Save often. Save early, my friends. All right, save to cloud. I'm sorry, I'm going through all this different battle music. Okay, terrible host. All right, I think we're done for the day. All right, save. All right, it's done. Groovy. All right. Well, thank you all for anybody that stopped by and anybody that managed to be around. Hey, Poindexter, we're just locking up shop for the evening. Yes. Oh, hey, go sane, insane, whatever it is. But all I know is right now, I'm gonna go hit the hay and whatnot. So other than that, we should be back tomorrow to work on some more stuff and things and see if we can't discover something neat. All right. Y'all take care now. Peace out, everybody.